Yes, so this question says, determine the approximate area under the curves of the following graphs, then interpret your answer. So here you have a graph, an example of the graph, and you've got a curve. As you can see, it rises, reaches a maximum, then it descends, and then you've got a shaded area from -1 to +3. Okay, now we need to take note that the line or curve that you see in any graph depicts or illustrates the graph of, or the behavior, sorry, of the y variable as the x variable is increasing. So very commonly, you will see the letters x and y in any maths class that you go and in any graph, all right? But you must always bear in mind that x and y are potential variables. Every symbol you see in an equation or graph represents a potential real-life variable. Okay, and if you have an entire equation, it says so to describe the relationship between them in the real world. A graph also says to depicts the relationship between two variables. Okay, an XY graph. Y, the vertical axis, the vertical variable, X on the horizontal axis, the X variable. Y is normally the dependent variable, X is the independent variable. The dependent variable depends on the independent variable. And the line that you see shows the behavior of the dependent variable. So if we call this variable Y, this vertical axis Y, then as you can see, Y is increasing from -3, for example, or -2.5, Y is increasing, but increasing now, the steepness of increase is decreasing, but it is increasing. And then the Y reaches a maximum, that's the maximum value of Y. And the value of Y now decreases. From 1 onwards, the value of Y decreases. So this line shows you the behavior of Y, how the Y values are changing, while the X values are basically increasing constantly from left to right, okay? Now, X and Y are normally general letters for potential variables. Now, if you choose to label X variable time and your Y variable, let's call it velocity, okay? Or acceleration, let's put the acceleration instead of velocity, let's put acceleration. So this line will show you the behavior of the acceleration as time increases. So from a given time value in the past, most likely the acceleration increasing, increasing. 0 could be the present, and it's still increasing, it reaches a max, and acceleration is decreasing. If you decide to take on acceleration, and let's say you put distance, distance is in meters. So here, distance is increasing as time is increasing, distance is increasing from a particular reference point. The distance increases, which is a maximum, and then it appears that the particle is moving back towards the the point of origin, because the distance from that reference point is decreasing. So here it comes back to where it started. Okay, if the Y variable was distance, if the Y variable was let's say speed is increasing. So as you can see, it depends on the variable that you define. Speed would be meters per second is the variable that you define what Y would be, and that would be the behavior of Y. The line will show you the behavior of Y, and the X, which is time in that case, is always increasing. Now we're finding the area. Again, the area, the interpretation of the area would depends now on what you define as the units, what you define as Y and X. So if you define the Y as speed, and you define time as t, the area under the curve would be distance, because distance would be an area S times t, because if you find the area here, we'll be multiplying speed times time. The area of this rectangle is the length, which is speed, multiplied by the width, which is time, speed times time will give you distance. So the area under this curve will interpret this as distance. And here, by counting these squares and approximating it to certain parts of the squares that are not so full, take one to make one, then we get approximately 49 meters if the y was speed and if the x was time. If the y was velocity, okay, if the y was velocity, okay, and you have time, then you'd get velocity times time would give you the same distance, because speed is basically a scalar quantity and velocity is a vector quantity. However, the calculation is basically the same distance divided by time. So a velocity times graph, the area therein would give you distance also. But if your y was acceleration, so as you can see, y and x are general, but you can define y to be whatever you are studying, what phenomenon, real world phenomenon you are studying, and the x to determine what real world phenomenon you're studying. So if your y was acceleration and your x was time, acceleration times time, that would give you the area under this curve, that would be interpreted as velocity. So the area under acceleration times graph would be velocity, meters per second. Again, you may define your y to be current and time, because here now, as you can see right here, if we have to use, if our variables of interest was current, charge, and time, charge in coulombs would be equal to current times time. Okay, so if your y-axis was current and your x-axis was time, the area on the current times graph would give you charge. So charge in coulombs is equal to the area of an IT graph. Okay, and here now, that would be approximately 39 coulombs if we're looking at charge. Okay, capital C, non-italics. Okay, apart from saying coulomb, we can say charge. Okay, if we're looking at current, voltage, and resistance, back to this here, 1 unit would be 1 coulomb. Okay, 1 coulomb. If we're looking at current, voltage, and resistance, then voltage now would be equal to current times resistance. Okay, so the voltage now equal to current times resistance. Okay, so voltage would be equal to the area of on the IR graph. IR means current and resistance. So you can have resistance in ohms in your horizontal, all right, ohms, and you can have on your vertical axis current in amps, and if you find the area on the current resistance graph, you can use capital I. Sometimes they use lowercase I or capital I, because you know lowercase I was also representing a complex and imaginary number, the letter small I. Again, words to symbols. We're using translate, transferring from words to symbol. Any symbol that you see is a word. It represents a word. V for voltage, R for resistance. Example. So volts now will be in volts. Voltage, 1 volt. So that's about 49 volts. So as you can see, it depends on what you define Y and X to be. X and Y are, you know, general letters to represent potential variables. And the area under the graph depends on what you, the interpretation depends on what you define as X and Y. And always remember, the line that you see shows the behavior of the Y variable. So in that case, if we're looking at current and resistance, as the resistance increases, the current increases from a certain value of resistance, whatever circuit. Sometimes you increase it. Although when you increase resistance, current is supposed to decrease, but sometimes there are other paths in the circuit that causes something else to happen, and then your, you know, your current increases, some kind of capacitor, whatever transistor, whatever you have. But after a certain point now, when the resistance reach, let's just say 1 ohms, then after that now the current starting to decrease, okay, to 0. Okay, so this shows you the behavior of the current, this graph, if we define Y to be current and X to be resistance. So always bear that in mind. Okay.